started. So this is week number, I believe, 4. Okay. And recall what we did last time, which was a little while ago now. So last time we did a few things, but we did things like cis of f, modulo of f comma g, and then f / g, this kind of thing. Okay. Every single one of these things you should think of as requiring a Grosvenor basis calculation. This one is actually the easiest Grosvenor basis calculation. You don't need to keep track of the bookkeeping for syzygies, but these both you need to keep track of some bookkeeping. Anyway, that's those are the main building blocks for doing this. And then we also did free resolutions and also computing Hilbert series and Hilbert functions and things like that from these. Okay, so today what I want to do is we're going to be talking instead about, well, not instead. I was going to do it last week also, but our modules, how to deal with them. And then this is going to be the first hour. Second hour, we'll play around with some of these things and maybe go through some of the problems if depending on what people have done or want to do. And on the final hour, we're going to do sheaves in cohomology. So sheaves on projective space and their cohomology. Now, the reason we can do that here, we're not even going to define what a sheaf is. We're going to use our modules and just sort of say how it relates. So if you know what sheaves are, you'll say, oh yeah, I remember learning that in some like Hartshorne level algebraic geometry class. If you haven't done that, then you'll say, oh, this is all it is. So so that's a useful, I think that's a useful thing. For me, it was really useful when I first learned. Okay, so but anyway, we're also going to do tensor and hom next in Tor, in part because this is going to need that stuff for some of it. So the first topic is how to represent a module. A module via computer. Let's say a finitely generated module and via computer, say. Or how would you do it in general if you were doing it theoretically? In other words, what is the data that you have for a module? Well, this is a non-trivial question, as it turns out. But one way to do it is one way, which is what we're going to stick with today, are generators and relations. We're going to have a finite number of generators here. And then we're going to have a number of relations on those generators, and that's what it is. If you think about it, this is a presentation matrix. So, for instance, what we might have is that's interesting. My notes have an extra 0 here on the end. I have no idea why. Anyway, M goes to, I'll say F and G here. F and G are free R modules. So they're just R to the A and R to the B or something like that. But they could be graded if free modules, if we're in the graded setting. Could be graded. And in fact, most of the time when we're dealing with all this stuff, they will be graded. Okay, that's going to be the main case that we deal with. But nonetheless, we have this. So this is really a free modules. I think of them as given by bases, and I guess I'll call this phi. So phi, let's say this is R to the. Do I have any specific names for it? I'll call this one R to the A and R to the B. This thing phi is an A by B matrix over R. So one way, and then M is equal to the co-kernel of phi. Okay, so that's just what this says. Now, here's the thing, is that if we can represent things via computer, if we can represent elements of R by computer, then we can represent these things. Just give ourselves a bunch of elements. So this is how we're going to do it. And here. So definition, this phi from G to F is called a presentation matrix for M. There's a few annoyances about this. One of them is it's not unique, and it might actually be hard to tell if two presentations give the same module. But anyway, that's that. So what are some examples that we are interested in? Okay, so if you're used to dealing with just ideals and things like that, if you do modules for your living, then this is going to be like not much. But it's kind of nice to see what kinds of things you're interested in. But actually, let's first start with our first example. So I is equal to the twisted cubic that we have done before. This is going to be the 2 by 2 minors of the matrix A, B, C, B, C, D in some order. I'll write this as F1, F2, and F3. And right at the moment, we don't really care the order, although it matters if you actually really look at it. Okay, so then this is a module. It's generated by R, and the presentation matrix is this R3 given by F1, F2, and F3. Okay, so that's a presentation module of R mod I. I is also a module. Oh yeah, this is one problem with this way of doing things is that how do you give I as a module if this is how we're giving it? You can't just say F1, F2, and F3. You have to give it by generators and relations. That is, in Macaulay 2, this is why we don't use this only. We use something more general than that includes both things. Well, I can mention that later. But in any case, so here, if I have I is sitting inside of this, okay, so this is I, and then this is going to, if I take a free resolution, the image of this map here is going to be I. So, in fact, if I take this to R2 here, and if you think about it, this was a 3-row by 2-column matrix, and if I choose it right, it's ABC, BCD. If I choose the F1, F2, and F3 correctly, this is the syzygy matrix on those 3 generators. Okay, we've done this one before, I think. But this is the presentation matrix of I. Okay, so this is the kind of thing that you want. Now, what kind of modules? What kinds of modules are we interested in? Kinds of modules of use. Useful. Okay, well, this is a loaded question because it really depends on what you're doing, and there's lots of different answers. But certainly, so the first one are R mod I and I. Okay, those are both useful modules. In fact, whenever you see a module and you're overwhelmed by all the language, just plug into the notion that M is equal to R mod I as a first run of understanding anything. That's pretty good. The second one might be I mod I squared. Okay, this is called the conormal module of I. Okay, so we might have to figure out how to make a presentation of this. In fact, we will. Another one might be Hom of an ideal into the ring R. This turns out to be very useful in certain cases. A lot of times, if you just do this, you're going to get R back again. So that's not useful. But a lot of times you don't, and those become pretty interesting. That's when we start talking about divisors and line bundle type things. That'll be really important. Actually, you can combine these two kinds of things. You can do Hom over R of I mod I squared, comma R mod I. And this is what's called the normal. It actually goes under the name normal sheaf or normal bundle, but that's it's this module, whatever. Okay. Ones we've seen already are X modules. And I would say these are really important, xi over calculated over R of R mod I, comma R. We'll talk more about general X in a bit, but basically we've already showed how to do this. You compute a free resolution of this, you just transpose everything and take kernel mod image. But you have to be able to do kernel mod image, kind of like you have to do I mod, something mod something. Okay. Another one that we're going to talk about later is omega 1 of R over K. These are the Taylor differentials, or just one forms. And then again, you could take the pth exterior power of this, and you get omega p. You get p forms. These turn out to be really sort of geometrically useful notions. Whether there's two ways of looking at this, but we're not defining it now anyway, so we'll worry about that later. These are already, when you think of modules, if you just think of all of these guys, you're in pretty good shape for the moment as far as getting everything going on. Okay. The only trouble is that we have to use these operations here sometimes to figure out what the presentation is. And in Macaulay 2, these are all under the hood. You just say kernel, or you just write you would just write I/I up arrow 2 for this. But it's good to know how to do it. So this way we're part of what this class is about. Okay. Okay, these are fine. Modules are great. They actually turn out to be really useful. I have to say I did not appreciate them when I first started out, but in fact they are really good. But really what we need are maps between these guys. Like we need maps like this. And maps of free modules are really easy. We can just write those down. But what about maps in general? So that's part 1. And then so 2 here is how to represent R maps, or R. I think I'll just use R maps. This means an R homomorphism, or a homomorphism over R, etc. And we might say, let's give this a name. Let's call it F from M to N. And for us, M and N will be finitely generated R modules, and we will typically have with a presentation. Okay. Don't necessarily need it, but what we'll have is that. So how do you represent these things? So what do I mean by that? I want to figure out the data I need to say what a homomorphism is from here to here. So we need to, they will be finally presented. So okay, that's a good question in a sense. Okay, so the question is wait a second, you said finitely generated, does that mean they're finally presented? If R is Noetherian, which all of the rings we are going to deal with for the moment are, then any submodule will be finitely generated of a like if I take the kernel, I will get that. So they will be finally presented. However, in my mind, I'm also just thinking of K is one of our standard rings that we start with. A polynomial ring modulo and ideal, that kind of stuff. Okay, and then those are all Noetherian. But in general, for Noetherian rings, we are assuming that R is Noetherian in general. Okay. Otherwise, we don't get these finite kind of things, and we have to be a little more careful. Okay, so how do you do it? So if I want to do it, so here, suppose I have M to N, and now I'm going to write down sort of notation for a presentation that I might use. Actually, no, oh, shoot, I wanted to change my notation to match some other stuff. Okay, this is going to be interesting. I want to call this F from B to C. and B and C are going to be finitely generated R modules. Okay. And so otherwise I get into naming conflicts. Okay, so here is my map from B to C, and it's going to be called F. Okay, now I'm going to write down a presentation for B. Okay, and one for C. So it's starting with some free module here. Now, just for the a lot of times, just in order to avoid having lots of notation, we're going to use B sub 0 and C sub 0. These are free R modules. Those will represent the generators of those things. And then B itself is going to be, these are all free and these are all free. And this is going to be C1 to here. And I'm going to call this matrix B, and I'm going to call this matrix C. And now I've just changed notation from my notes, which is going to be fun. But at any rate, we have this. And so this is our input data, really. Oh, not really. We're trying to figure out what our input data is. So what is F? Well, actually, in some ways, because of the projective property of this, I can certainly lift this to here and then actually lift it to here. So I get the map from the generators to the generators, and I'm going to call that F0. Okay, so is everyone okay with this? So it's important. So every homomorphism here is determined by what happens on generators, and then how it only depends on how it goes to the generators. There might be lots of ways of representing this, but you can always find one way that does it. Okay, so F0 is this thing, and now what do you need for this to be a what F0's work for this to descend to a homomorphism here? Any what do you need? Yeah, the relations are satisfied. If I have something that's 0 here, it better go to 0 here, okay? Or it better go to 0 here. So in other words, what I need is we need for F to be well defined. We need that that if I compose these two, F0 times B, okay, so I do B first and then F0, I want it to be in the image of the C map, okay? Or another way of saying that is we had the F0 composed with B. If I take that, which means take every image element and present it with respect to the matrix C, this should equal 0. Okay. There's another way of saying it. This is the way we'll actually use it. So we will typically not. What that really means is that this thing here is in the image of this. So we could write an F1 here also. Okay, such that this commutes. That's exactly what it is. This is going to be one where you have these two things where this commutes and then you're fine. However, we never really need F1, and so we don't typically compute it. Sometimes, but typically we have to check a minor amount of stuff. So we don't usually compute F1. Could if we felt like. Anyway, that's the information of a module R map. You have to give 3 things. You have to give B, F0, and C. Okay. And then you can start computing all sorts of stuff with it. So let's do a couple examples of that. Okay, actually, could you hit the button for over to here? So let's do a couple examples. How are we doing? Okay. So A, given F from M to N, find its kernel. Okay. So find a map. When I say map, I usually mean R map and so on. So find a map, which I'll call cis of F, which is going to go from some free module haven't actually said what it is, so why don't I just say, and I actually already I'm screwing up. This is going to be A to B. Sorry, B to C. This is really bad when you get so used to your notation. Okay, so anyway, so given f from B to C, you want to this thing, which is going to be from a free module, f to some number, some question mark number, to B, such that the image of cis of f is equal to the kernel of f. Okay, those are both submodules of B. Okay, so how do we do that? So this is actually pretty good because we already know how to do a bunch of these kernels. If these are both free, I just do cis of it, and that's a straight Grosvenor basis calculation. If I go from a free module to C modulo something, a free module modulo something, that, surprise, surprise, is the modulo command, which is sort of where it kind of comes from. But anyway, and so we know how to do that. The only trouble is if this is now not free, how do we do this? Okay. On the homework for this this week, we talk more about this because in reality, if you think of it, so on the homework sheet, I think I kind of did it. I made some changes at the last minute to that, and I have to maybe redo it because I left a bunch of typos and just misformatting things in. But at any rate, on this is you might want the kernel map. So what I want to say categorically in category language wise. So you might have B mapping to C. This is F. And now we want the kernel of F is going to be a monomorphism from here to here, or injective map. And but what does it satisfy? It satisfies that whenever you have A, so given A, so first of all, it's some map here, eta. Okay. So I'm basically just defining what the kernel of F is categorically. So you probably could all just sort of sit. If I put you in a room by yourself, you could probably just do this. But we'll just do it here. So given a map from here, let's call this G. Given G from A to B, such that this composes to 0. So that is equal to 0 here. So that means that I do G first and then I do F, I get the 0 map. Okay. Hopefully I can tell whether I got a 0 map. But anyway, suppose I do. Then what do we know? Then there exists a unique map here. Let's call it, say, G prime. There exists a unique G prime from A to the kernel of F such that G is equal to, first do G prime and then eta. So this factors through. Okay. It's all very well and fine to say this. Oh yeah, this is pretty obvious. Now I want you, as the homework, is you have to actually find this map. You have to find the map eta and this map. So that means using cis and all this kind of stuff to do this. On the homework also is the co-kernel, which is just the dual of this. When you put it here, and then you don't have maps going into it, you have maps coming out. And but I actually stated what it is exactly. And then there's those are two really important universal properties, one for kernel, one for co-kernel. And then there's the co-image and image, which is also mentioned on the thing. And then once you have the things that we do there, basically you have you really have modules as an abelian category. And we've implemented it at that point after you've done that problem. So so anyway, it's kind of fun, so you can take a look. But I'm not going to go into that now. Okay. But anyway, so but right now, let's see how can we do this. Okay, this is a little more involved than this because this I'm just giving you kernel of f. Here you actually have to get the map in. It's actually pretty straightforward, but you know, it takes a little while to get it right. So it's a good exercise, I think. Good computational exercise and also just thinking about it. Okay, you have to think about some of these universal properties in a slightly deeper way than you might have had to worry about in the past. Okay, so anyway, so how do we so let's find so here let's find a presentation for kernel of f. Okay, so kernel of f is going to be some submodule of this, but we want to find a presentation. Okay, so sure, I'm going to write down some stuff. Here's B to C. I hope I have enough room here. I think I do. This is B0 to C0. And this is B1 and C1. So these, remember, these are all free modules. This one we don't care about. This is F, but we're given it by giving F0, given the matrix B and the matrix C. Okay. So, so how do I calculate the kernel of this? So I want the elements in here that map to 0 here. So any suggestions? For instance, let's say we have F is going to be a free module here. Okay, F and the B sub I and the C sub I are all free modules. What is this map here? That will so I want the image of this map, and actually it really is this kind of that's what I'm trying to do right at the moment. That's different from a presentation of that. So I want this map. So what is it? Well, how do I tell if something? So I want stuff that's in the kernel from here to here, but that is just B0 to C0 mod this. So this map here, write it down. This matrix here is modulo of F0 comma C. Okay, let's give this a name. Let's call this G sub 0, say. So G sub 0 is equal to modulo of F0 comma C. Now what? So that is actually this map here. So this is of that F is all it is. Is this okay? Is this understandable what I'm saying? I'm getting some nods, but I'm also getting some people not giving me eye contact. Anyway, but if you think about it, so the image of G0 is equal to the kernel of the map from B0 to C, okay, which is given by either direction. Okay, well, anyway, that's that. Does that map onto the kernel of this? It sure does, because the kernel of this and kernel of this are the same thing, because these are both the same map. So anyway, we have that. And now, but we want a presentation of this. So what do we do next? We want a presentation of the image of this thing here. Well, not really. We want it down here. And I did really screw up my language. I put this exactly where here is kernel rats. Boo-hoo. That was stupid. I'm going to move it. So I'm going to have the kernel of F here is what I want. Okay. And this map here, I'll just do it like this. This is G0 is equal to modulo of F0 comma C. Okay. And I would like to claim that this maps onto the kernel of F. So this is a surjection onto that. Well, I mean, everything that's in the, if I have something in the kernel here, it certainly comes from here. So it's a diagram chase kind of thing. So if I have an element of the kernel, which is going to be in there, you lift it to here, but that goes to 0 now, and therefore it's in the image of this. So then I actually can take this thing and I mean everything. If I just take this map to here, the image is the kernel of F. Where's little k? KER for kernel. No, there is no k inside other than that. Okay. So anyway, but we need actually, that's just the generators. Now we need the presentation of it. So what is that? So you have to think, these are not completely trivial to think about. I mean, even when I was doing it on this weekend, doing this thing, it took me ridiculous amounts of time to code this up in Macaulay 2, even though it's only in the end 3 lines essentially. Okay, but if you think about it, this thing here is the map you want. It's going to here, and I want the kernel of that map, right? That's it's mapping to my kernel, and I want the kernel of it. That is just the kernel of this, but that's F going to this modulo this. So in fact, if I let this be now G1, which is bad notation maybe, and now I had G0 as that, and now I have G1 is equal to modulo of G0 comma B. And that's the presentation matrix. For kernel of F. Okay, so you do 2 things. You calculate one modulo, so that's one Gribner basis computation plus keeping track of some syzygies, and then you do another one. And it involves exactly F0, B, and C, exactly the data we need for it. So this is the kind of thing that you can do with this. And I would say almost all of them are. This one uses not just this is just using modulo. Sometimes you get to use sys if you're lucky, because remember sys is only for free modules, and you're taking the kernel. But it also is going to use the lift, the // here. Okay, so I'm going to leave that now because I think really it's important to do those yourself, and so I can especially tell that by looking at everyone's face when I'm just doing this one up here. Okay. Let's do one more example of this. Oops. Because this one comes up a lot. Suppose I have R to the A. Let's not use it that way. Let's just call these free modules. I have F, G, and H. I have F and G. F, G, and H are free modules. Okay, and it's a complex. So when I compose it, I get 0. And suppose F times, you do G first, then F, and you get 0. Okay, so these are just 2 matrices, and I'm just doing this. So find a presentation for the homology for the kernel of F. So the kernel of F certainly contains the image of that. That's what this statement really is saying. So if I want this, find a presentation for this module. This we do all the time, and so it's worth it to say how to do that. So any suggestions? Solution. This is like in undergraduate class. I'm just giving little nice little examples. Okay. So how do I do that? Okay, I need some more space over here because I didn't know. I strategically left out my not enough room to do things. Okay. So I want the kernel mod the image. Okay. So first of all, I need the kernel. So I would say, I'm running out of names for these things. I don't want to call them primes. I think I'll just use R to the, A or something like that. We don't have any matrices A's or B's around. So this is this, and this is what? This is cis of, this is F, right? This is cis of F here. It just maps, so this will map onto the kernel of this. So the image, actually, I don't want to write it there. So the image of cis of F, as usual, is by definition the kernel of F, if F is a map of free models. Okay, so we get that. And now what do I have? I have two maps mapping into here. This one, and then I have this one here. These guys, I want to take the generators of this. So this thing is going to be generated by A elements here, because so certainly any element in here is a quotient of something coming from one of those syzygies. But these are the guys that are zero. So do you know what the presentation then is of of this thing here? Let's call this let's just call it kernel of F mod image of G. Okay, so how do we get that? So we want the things here. We're going to take this modulo the image of this, and that's actually that's just a map from R. I want to think of it as a map from RA to G mod the image of this. So I really have R to the A mapping to G modulo the image of G. And now I want the kernel of this map. I don't know if I want to call that anything. This is, let's call this H, and this is going to be H bar, okay? Because H is just really this and then mod out by that. So what's the kernel of this? So this is the kernel. It's not actually. This is not the kernel of F mod the image of G. It's a bit larger because G contains the kernel. So I guess maybe I'm really tripping over my language here, but really what this is, this map here that we compute is modulo of something. So what is it? So it's the map H here, modulo this stuff. So it's H comma G. So that's it. And this goes to some R to the B here. And this is a presentation for kernel of F mod the image of G. So in fact, let's just write it down. It's modulo of cis of F comma G is all it is. So you have to, so let's think of, so if I take the kernel of F mod the image of G, it's certainly generated by these guys. And I just need to know what the relations are on all those elements. And the relations are on those elements are however, whatever combination you get in here that goes to zero mod this, which is exactly this. So this is it. So in fact, this one takes, to calculate this, it takes two syzygy computations. One here and then the outer one. That's actually a little annoying, to tell you the truth, in practice, because these can be pretty serious computation. So sometimes what you can do is, if you want this, you don't necessarily need the entire module. You can get by with the Hilbert function of it if it's graded or something like that. But then you only need to calculate this and then the Hilbert series of two things. And so you can sometimes use that instead of computing that. Actually, this last one is kind of annoying. It can be very huge. Okay, so let me ask, does this make any sense, and is this okay? No? Okay.
I have no bet.
Okay. Let me, you know what? I think what we'll okay, that's good. No, that's a good question. How about other people? I did. No, I think actually other people had rough time too.
Why not assume G is a certain G? Because G could be why aren't you restricting?
Well, typically I have maybe we should do it by computer and I can just take a look. I'm not sure that would help out. I have to think about it. Maybe during the hour, when we take the break, I will try to do a better job of this. But maybe I should first of all state this as a result or something like that. Actually, I'm not sure if I'm going to be able to make it much better. Okay, so yeah, actually, let's do an example of it by computer. Okay, I have to oops, I have to join Zoom. Shoot. There's the Zoom link. Okay, now I'm going to share. Oops. Okay, hopefully it's now off. Okay, let me share this. Okay, that's too small. Just a second. Oops. Is that visible? No, I can make it larger that way. Ah. Okay. What did you say? Oh,
I was just thinking.
oh, I see. Right. So let's take this to be ZZ mod 101 of A dot div D. Okay. This is going to, and then let's take I to be the where we can get an interesting map like this is if I take the R comma. It's interesting, but it's not too big. 1, 3, 4. 1, 2. Wait, so 1, 3, 4. It would help if I finished the word. Monomial curve. Okay, so here's the ideal. Let me make this a little larger over here. Oops, that was maybe a good idea. Is that readable or not? It's for people in the room here. Online it's probably a little easier. So so if I have that, and now I take I'm going to take C is going to be the resolution of, I'm going to take S to the 1 R to the 1 mod I. That's the same thing as doing res of I res of I, but it's a little more thing. It's a little more honest. Okay, so C dot DD, these are the maps of the resolution. Now the ones I want to take the last two matrices, and I'm going to transpose them. So we're going to be calculating X module type thing. But what I want to do is take these two things. Now, what did I call these? F and G? So I'm going to say F is equal to is going to equal transpose of C dot DD underscore 3. Let's see what that is. That's a pretty easy one. So it's just 4 variables with some signs on it and kind of mucked around. And then G is going to equal the transpose of C dot DD underscore 2. Okay. And there's 4 guys there. And now what we want is let's first of all check and see. In order for this, I want to do G first and then F, and I get 0. Okay. So this is a good example of one of these things. So let's write down what it is on the board. So what we have here is we have so what are the numbers that we have? It's R to the 4. That's going to be my F, and then this is R to the 4 coming in, G. Okay, this is what we have in the example. And what was F equal to? Let's just write it down. We won't write the other one down. Is D minus C minus BA or just B? Minus BA, okay, for whatever it chose, okay? And then this is, these are 4 generators that are going to be in the kernel of this thing. And what we want is we want something that is, so we want the kernel of F mod the image of G. Okay, so let's just think about how we would do that. The first thing we need is we need the kernel of this. Okay, so that's going to be R to R4. And now if I do sis of that, I'm going to get the generators of this. Now, if you're familiar with this, you're going to get how many generators? Each one is going to be of length 4. And I know a bunch of syzygies on this. If I take any pair and I just I take the Kazul syzygy, the trivial one, where I just change the order. Like for instance, if I do the first 2, that would be C here, D here, and 0, 0. That would be one of them. And then I have a bunch more. It turns out I have 6 of these. And we can see that here. So if I take sis of F, I get, in fact, 6. In fact, the first one is CD 0, 0. Okay? So that's what sis of F is giving us, is just the matrix of the kernel of these. Now let's write down at least 1 or 2 of these. Okay? So the first one is probably, here, let me just do this up here. So the first one is minus B squared minus AC minus BD and minus C squared. And let's write down the second one too. CD 0, 0, and then something here and something here. Okay, right? If I didn't make a mistake. And so what do we know actually? So we have all these, we're going to have 6 generators for our kernel. And then we want to figure out what the relations on those 6 kernel, those 6 things are. Okay. So so the kernel of F is really the this I think I called H over there, right? So this is the kernel of F equals the image of H. Okay. So now we can ignore F completely, and we just have these things. Maybe I should write a couple more down. Can someone just read the second one of these? If
B minus sorry, you're doing that one.
Is it on there?
B0 D0.
B0 D0. Okay.
You want more?
Yeah, sure. Why not?
0B minus C0.
0B minus C0.
Yep.
And then there's one more, right? No, there's 3 more. No, well, let's leave it for the moment. We might need them later. Okay. So so anyway, so we want these 6 generators here, modulo these 4 generators. So one way to think about that is you put this in a big matrix, CD 0, 0, 0, B 0, D 0, and you keep going, and these are the 6 generators of the syzygies of F are right here. Okay, these guys here. Okay, but now I have these guys I'm setting to be 0. So I'm going to put those over, and I'm going to make one big matrix here, minus B squared minus AC minus BD minus C squared, and then I'll keep going, CD 0, 0, and I have actually 4 here. And these are going to be 0 in my module. So my module I think of as kernel of F, which is these 6 generators, modulo these 4. Okay. Now, how can I tell what the relations are on these guys here? So I have 6 elements. A presentation matrix is going to be the relations on those 6 guys. Okay. So we want the relations on these six generators. Mod the 4 generators of the image of G. Okay. So for instance, this generator is 0. It's already over here. Okay. This generator is, I don't know if it's over there or not. We'd have to write all those down. Maybe we should write a couple of them down because it's, so in fact, let me write down, I have C, D, 0, 0, and then A, B minus C minus D, and then 0, 0, A, B. So this already is telling me some interesting things. Even if I don't do any more computation, what have I computed so far? Well, I've got these two maps, but then I also found the kernel of this thing. So now what I do is I have 6 of these guys, 6 of them, but in fact, these 3, these 2 in particular are going to be exactly 2 of the ones here, right? I think we wrote that down. We didn't write them down, but these are all whenever you have pairs. This one is actually the sum of 2 of these guys. Maybe I should write more of these down. I'll keep the same notation that this is using. So 0b minus c0, this is going to be a 0, 0 minus d. And then 0, 0, a 0, c. And then this is 0, 0, ab. Okay. Fine. And now that's what's up here. So these are our 6 generators. So what this is telling us is that this one is 0. So it's not going to, we don't even need it as a generator. What other ones? CD, well, that's it. That's the one. AB, that's the last one. We don't need that one either. AB minus C minus D, this guy here is a little more annoying because in fact, it's a sum of these 2 or some, the sum of these 2. Exactly that, right? So the sum of these is 0. Okay. Now, this modulo command, what is it really doing? It's taking the syzygies of this entire matrix, and then it's just looking at this part of it. So it's basically what combination of some of these things is in there. So that's exactly what we're doing here. So that's why modulo is sort of a good thing. But what we could do is we could put these together and just try doing the kernel. So if I do, let's call this H. H is syzygies of F. And if I take matrix of H comma G, I think, right? Let's see. So that's, in fact, exactly the matrix that we've got up there. And now if I do sys of that, sys of OO, I get all of these relations. And now if you think about it, so each column is a relation, right? And the first 6 are going to be the parts of our generators, and then the last 4 are all going to be 0 elements in it. So if you look at that, the first 3 are telling us that our 3 guys that we saw here are all 0. So we only have 3 generators left. And then over here, this one, this B minus CD is actually an honest to God syzygy. It's going to be a relation on those first 3 generators. And then the next one is also going to be a relation on the first, on 2 of this generators. Actually, only 2 of them. That's interesting. And then 1, 2, 3, 4, 5, 6. This is an, oh no, sorry. Here is an A, C, D. So it's a generation on all 3. Yes, question.
This might be stupid, but are we always guaranteed that the bottom 4 rows there are going to be full rank?
No,
Okay.
not at all. In fact, they don't even have to be constants. It could be much more complicated than that. In fact, I'm a little surprised that it's not a little more complicated here. Okay, but in any case, so what we have then is these last guys are not getting rid of any new generators. But what they are doing is they're giving us relationship on our 6 generators. So we have, so in reality, if we don't want to just do X's on those things, what we would get is we would have this generator here, this one, we would have 3 linear relations, and then these 5 guys here. And if I do modulo of H comma G, that's exactly what I'm getting. I'm just getting, well, except for the signs, okay? So in fact, the order, yeah, no, it's the same, except I don't know why the sign is coming out different, but in any case, it is. So, but it's exactly the same as this thing here, but it is in a slightly different order. That's because it's doing a slightly different computation. Okay, so what this is saying is that we've computed cis of f as this, and then the presentation. So if I take the kernel of f mod the image of G, that is equal to the image of H mod the image of G. And this has presentation matrix modulo of H comma G. So this is the way. And I should not have, what I just did was very disingenuous, because when I am in my mind seeing those things, this is exactly what I'm seeing, this kind of thing. I'm seeing exact matrices and trying to figure out what the relationships are on them. And then doing this without any actual matrices is not, I mean, you write it down that way maybe, but in your mind, you're thinking of it like this. Is that any better at all? Or so-so, right? Anyway, it's followable. It's going to be worth checking out, because if you want to do anything with modules, this kind of just getting used to how you compute with them, doing syzygies and things like that is good. Now, in reality, you don't need to do that here, because I can type in the following. I can do kernel of f mod image of G. And it gives it to me as a subquotient, which actually we haven't talked about. But if I prune it, it will give it to me as 3 generators, and it'll get rid of the ones I don't need. Okay, so in reality, if you want to just use it in Macaulay 2 or something, you don't actually have to know this. But if you want to know what it's really doing behind the scenes, it's exactly this stuff here.
What is O?
O is always the last one. So in Macaulay 2, all the things are labeled O sub 1, O sub 2, O sub 3, and you can use those values unless you remove them. And but OO is the last one. OOO is the one before that. I don't know how far back it goes, but it only goes back a hand. But it does go back at least 3, I think. So, but it can be really annoying because you're using that, and then all of a sudden you do something else and you want to go back, and it's just a mess. So so it's not always a good thing to do, but here I tend to do it. Questions? Yeah.
What's the shorthand you just used?
Oh, here, let me put that in the thing here. It's this line here. So I do curve f, which is how you compute the kernel, and image of G calculates that submodule, and then it knows that they're both sitting inside the same thing, so you can do a slash of it, and it calculates the module, but it gave it to you in some weird way as a subquotient, which is really the image mod image, which is actually just giving us those 2 things there. But prune will then figure out what the presentation matrix is and maybe remove non-necessary ones and things like that. Yep.
What kind of objects does prune act on? Like what is its like maximal use?
So prune works on any module, but it also works in other situations. If you prune a ring, it will try to get rid of linear generated variables. So if you have a ring where you mod out by x minus y squared, it will try to get rid of x and just give you the ideal in a new ring with 1 less variable. So that does that kind of stuff. But it's sort of meant to be minimal presentation. But it only is minimal if it's homogeneous or if it's graded in some sort. Yep.
That does her F on image G do everything we did in the background?
Yes, absolutely. So curve F does a cis because it's a free module. It will look a little more complicated because it's handling also the cases where it's a subquotient module and whether, you know, and it's cis anyway, so it's handling more situations. Actually, we can probably even look. If I do methods of cis, and there's cis of matrix. So if I do code of 1, I believe that will give me the code. And here it is. And if you look at it, what it's doing, I don't know why there's 2 things here. Oh, it's running hooks. Okay. So anyway, it's doing this. First of all, if it's not free, if the source and target are not free modules, it says you are using the wrong command, you know, and then gives an error. And it says if the ring is the integers or not homogeneous, then it does one thing. It basically takes a Grosvenor basis of the columns of F. In both cases, it's taking a Grosvenor basis of the columns of F, and it says, I want you to be computing syzygies while you're doing the Grosvenor basis. Okay. And then sys of a Grosvenor basis is just pulling out the stuff that was collected for that. And then the min-gens is actually minimizing it. But the sys of GB is exactly what we were doing. One Grosvenor basis, but it was a Grosvenor basis where you told it to keep track of that extra information. So that's that. And then modulo is actually pretty similar. If I do methods of modulo, and I do code, matrix, right? Code of 2. So what this is doing is, again, it expects some free modules, and otherwise it also expects some degree stuff. Okay, so ignore that. And finally, so it's doing a bunch of checking and crap like that. And then here is the main command. It's doing H is M concatenated with N. That's exactly what we did here. M concatenated with N. But now when it you tell it to compute syzygies, but you also say, I only want that parts of the syzygy that involve this number of guys. So it computes that, and that can make it a less intensive computation. Okay, and then it packages it together. Okay, so modulo is just concatenating those two matrices and doing a Grosvenor basis, one Grosvenor basis computation of that whole thing, which actually could be easier than Grosvenor basis of this, but it could be also harder. So it's sort of it's that way. Okay, any other questions? So the basic idea of this is that the main operation is syzygies. and if you can compute those and you start thinking of it, all of a sudden almost everything you want to do with modules involves syzygies. So there's question online.
So I want to take the course for credit. I haven't got the homework list, the homework sheet.
From when?
I mean, I haven't got the homework sheet at all.
Here, why don't we talk about it after we start doing projects or something? I'm not sure what you're saying exactly.
No, I did not get the homework sheet at all.
It's on the course.
It's on the course website.
Like the lecture.
Okay.
Okay. I see what you're saying. Okay.
Okay, I'll ask. Okay.
I want to, before we break, I want to do one more thing. Okay, this will be good for the also for one of the problems in the project section. Okay, so here is the question. I want to talk about Hom and tensor. So both of these constructions are really important. If you want to be able to compute with modules at all, you want to be able to do these. And let's first do so I hope you all remember Hom and tensor. However, so what we really need is the proposition. This is so I want to recall exactness properties. Of Hom and tensor. So one of them is left exact, one's right exact, that kind of stuff. So, but it's important to just be able to write it down. So what we're going to do though is I'm going to give you a, so this is in the T. McDonald. Actually, it might be an exercise at T. McDonald, I forget. But anyway, suppose we're given a exact sequence. 0 goes, and I'm gonna write it backwards, so this actually really does mess with the left versus right thing, but I can never remember what left and right mean anyway, so you know, it's a Stillman left as opposed to, okay, so anyway, so M, and I'm gonna have two other modules here, M0 and M1. And no, actually, I want to do it differently. And we'll just do it this way. Okay. And so I'm going to give you a exact sequence like this. It's not exact at this side here, so it's exact all over here. And let's give this a name. I'm going to call it F for the moment. Okay. Then we have two things. So here M, M0, M1, and eventually N are R modules. For me, they're all finitely generated, but I don't think you need that here. So then, so given this is exact, but not at M1, so exact wherever there's one going in and out, then A, if we apply the functor HOM over R of dash comma N, okay? That's one of our R modules. We do that, what do we get? Okay, you have 50-50 chance to get the what order these things are done in. So we're going to have HOM of M comma N. That's one of them. Here's going to be HOM of M0 comma N. And here is HOM of M1 comma N. Which way do the arrows go? So if I have a map from M to N, so I have a map from M to N. Actually, once I have a map from M to N, I get a map from M0 to N by composition. So this is the way the map goes. And similarly here. And actually a 0 here is we get this, okay? So we at least get this complex here. And the point of this is exact. But not at this point here. So all this stuff here is exact. And then B, if we instead apply tensor over R with N, what do we get? Here we get M tensor over R of N. That'll map to, that'll be 0. Actually, this is when you don't have to worry, it never changes the direction of the arrows. And then this one is M0 tensor over R of N. And then here is, here, I'm going to actually, people can't see this so easily because of my screen sharing. Okay. Can you all hear, can you all see my screen now?
Yes.
Okay. So, so if I'm just applying N, so I get N M1 tensor over Rn. And these are just the induced maps, F tensor, the identity on N, basically. And these are also induced maps. So I guess I would call this HOM of F comma N here. And this would be F tensor N. And this is exact. Except at the ends. So, but not on the right. Here and here. Okay. So, okay, this is all this is just categorical nonsense, right? I mean, you got some right exact, this makes it great. You can now do derive functor things and so on and so forth. In fact, that's how you're going to get X and so on. But in reality, this is awesome because this is how you compute these things. Okay, look at this. If this is actually a presentation, M0 and M1 are free. HOM of something into that, that's just going to be a number of copies of N, a direct sum of N with some number of copies. Same with this. And this is saying that's the kernel of that map. And I know I can just write this map down in that case, and then I can take the kernel, and that's going to give me at least a set of generators for this. Okay. Similarly here, if I have a presentation here, I actually get a presentation for this on the nose with no effort. So the cool thing these allow us to compute of m comma n and m tensor over R n. On the so the one with if n is not R, it's a bit of an annoyance, truthfully. Okay, yeah, you don't like that modulo and cis, you aren't going to like any of these things. I got to tell you, okay. But this m tensor n, there's no computation here. This is a presentation matrix of it, and if you just think about it, so one of the problems I gave on the week 4 problems is just to in a very simple case, just write it down, because once you see it, then you got it. So so tensors are quite straightforward, whereas and if this n is R, this is just the transpose of F. Okay, so that's all that is. So this allows us to compute, also allows us to compute POM of I comma R over R. And that's usually, we'll call it I star. Okay? Actually, or M star, it's the same thing. POM of over R of M comma R. Now, last time I said something about trying to compute the map from M to M star star. I don't know if anyone tried to do that problem. But this time what I did was I actually left it on there, but when we were doing this thing here, it turns out that these computations are really useful for that. So if you think of that in that terms. So I have Macaulay 2 code that computes this double dual map, and it takes a handful of these cis modulo lines. Okay, so but it might be worth trying to puzzle out, especially since this one doesn't. Once you have to hum with n, the n has a presentation, it's just a big mess. But although you could do it. So I think I want to start one example because it's one I would like to take a look at during the break or after the break. So R is going to be a polynomial ring in 4 variables. This time I chose x, y, z, w. I don't know why. Except I'm actually going to mod out by x, y minus z, w. Okay. By the way, how do you calculate in a ring like that? Can I compute syzygies in a ring like that? If I have a free mod, you know, I mean, I'm modding out by something. It turns out you could just lift it back up to the polynomial ring, and over in the stuff that's 0, you could just put a whole bunch of copies of x, y minus x, y minus zw in each, like an identity matrix times those. And then that allows you to compute in there. It's done a little more efficiently in Macaulay 2, but basically that's what it is. So in other words, working in a ring like this, you really are thinking of, you're working in here, but you're just sort of, as you go, are just making sure you reduce mod this. Okay. Anyway, there's that. And now if I look at the 0 set, we haven't really talked too much about 0 sets, but if I take the 0 set of x, y minus zw, this is going to be a quadratic. I'm going to call it Q. It's homogeneous, so I'm going to say it's in projective 3 space. You could say it's in affine 4 space if you wanted, but since we'll be doing lots of this, so this is a projective 3 space, and this is a quadric. And now I'm going to take an ideal. I guess I called it J here. I'm going to take an ideal X and Z. This is an ideal that contains this thing, so it descends to a nice ideal in this quotient. And the questions I want are what? So I want to find A is a presentation for J? Free resolution of J? As an R module? This is as all as R modules in here, so I won't even say that. And then also find a presentation, or find it as a matrix, I should say, presentation of HOM of J comma R. In other words, this guy over here, the dual of it. Okay. And then also on there, this is going to be some module. It's going to also be isomorphic to an ideal in here, up to a degree shift, but we don't worry about the degree shift. And so I want you to find that. So that's on the sheet. You'll see. And anyway, this playing around with this, I think, will be just a good way to get sort of experience with all this kind of stuff. It's you're doing it over this, so it's a little more okay like that. But actually, think about what this is. This thing here, what is V of J? Well, it's going to be set into side of Q. Okay, so it's going to be where X and Z are 0. That's a line. So this is a line in 3 space. And it's a line on Q. Okay, so it'll be interesting to see what you're going to get an ideal from here as well. So what is it? So the same thing, something different. So I recommend that after the break that this is a good problem for us to work on. And that's I think the first one on the list. I might change up the actual problems a little bit after that because, well, we'll see. Any questions about that? It is now a little late. Let's take a 15-minute break, and then at 11:35 can work on that. And if so, yeah.
This is maybe a silly question. What is a presentation?
Presentation is just that matrix, so that gives you the kernel. The co-kernel of it is the matrix, the module you're interested in. So it's giving a module by generators and relations. So the presentation itself is the presentation matrix. The presentation itself is, you have presentation matrix, or you say fix a presentation. I don't know. I guess it's the same. It's a synonym for it, but it's a matrix whose so the number of the rows of it correspond to the generators, and the columns are the relations on those generators. So that's exactly what all of that is. So for instance, do you guys want to think about this yourself for a bit first, and then we can talk about it? That's probably better than me doing it. So did you have a?
Well, I sent you the URL.
Oh, you did. Oh, okay. Here.
Yeah, so, but I'll have to try that, like, because it looks like you were actually running a Python project. You were starting at the Python instance. So.
I'm not sure. Maybe.
Well,
I don't think it is. I mean,
so-
I'm a little unclear on that.
okay, so-
We make our own kernel, and it's
okay, so this is you're just creating a virtual environment.
yeah, that's
This
right.
is your starting, so now you've got,
Well,
commands.
basically, when we install this
Yeah.
kernel,
so you won't
You
have
want
to
it.
clone the repo anymore. You'll just have to, you just have to pip install, like you start your virtual
you do pip
environment,
install and something like that,
the
right?
big URL, this URL. You see, like this is, so if you're on the
yeah.
main branch, you would just give it the name
Yep,
of the
sure.
repo. If you want a particular branch, you stick this on.
Right. Okay.
So this is the install command, so that's nice. You don't have to like.
But you have to,
And
like
then-
on the Mac, you have to, or at least the current Mac, this won't work as such because it will complain about installing it. That's why you have to do the virtual environment.
No, that's right. Yeah, you're still
Yeah.
gonna create, you should always create a virtual environment.
Yeah, right,
because
okay.
You don't want to screw up, like the system.
Yeah, right, right.
So you always create a virtual environment, but then you install this. Now, this is the only
thing I'm not unsure of, like, so maybe this is like running a server in the background. I'm not sure, but normally when you
I
run
thought-
command,
Yeah, that's and
oh, you know what, it may, yeah,
I think
because when you
it's,
create a notebook, you actually specify which kernel you want to use. So maybe this is just sort of adding.
this, I
Can
think
we
this
call it-
line is just adding to the list of kernels for
That's right,
Jupyter.
yeah.
And I don't think you can do it in the pip install because it's actually installing it in a more global place on the computer.
Pip install just puts that Python code in your Python
Right.
virtual environment. But then this probably.
I think that writes it into your
probably just says this is
your
this is
slash
the
u-
kernel. And then when you start your notebook, when you create a notebook, you pick a kernel.
That's right, exactly. And I don't know how to
I'll try.
yeah,
It'll be
good.
mine.
yeah, no, that's actually great. That's good.
I use the JetBrains. I mean, VS Code has gotten, it's getting a lot of traction,
Actually, I'd be happy if it were,
but it shouldn't really matter.
no, it shouldn't.
So the guy who's behind VS Code, like the latest VS Code, is Eric Gamma, who used to work with me at IBM.
Oh, yeah.
He's a really great guy.
Okay, cool.
He's an expert at IBM. He did, like,
I find
worked with-
VS Code I mean, I'm kind of an old hat Emacs kind of
No,
guy,
it's-
but in reality, people are not really willing to learn it so much anymore. Some people are, but overall,
I know these young kids.
but VS Code, everyone tends to use for other things a lot of times. So,
Yeah, it's very-
Jupyter notebooks are also, I think, good. But what I really like is that you can do Jupyter notebook instead of VS Code, and it actually, it seems to work very
You
nicely.
can also run Jupyter notebooks inside the JetBrains side. But I don't know, like, so far I like running, running it in the browser.
I felt like that.
So
Okay.
so one of the advantages, I don't know if you've actually done this, but if you're writing significant code in your notebook,
Yeah,
the debugger in the IDEs is better, like it's easier to debug. If you're running it in an IDE environment.
I see.
If you're just running it in the browser, you really can't debug it. I mean, there's no.
yeah. I mean, there's a Macaulay 2 debugger also, and I think you lose all of that in here. You don't. In fact, I think it's run with minus no debug or something, so you can't even run it. So I personally find that to be a little annoying, but maybe we could get that to work too. That would be nice.
Macaulay, ever do the Google Summer of Code stuff?
So, we have not yet, but it's been talked about.
I know
So-
somebody told me that they had a good experience doing it with Sage.
Uh-huh.
And
I mean, I'm subscribed to the daily list and like every time. Starts out. He likes the
I mean, there are definitely lots of interesting cases where running this stuff from Python would be nice. Although I find it much easier to write in the Macaulay 2 language than in any Python. But on the other hand, Python has a number of packages that are really nice. What?
You got here each Okay. Let's see if it works.
Okay, great.
Looks like it worked.
And they're using
Okay. There's no version of that.
ocean.
This is it.
That's all.
Oh, I see, okay.
Pip. Hopefully get this new pip. Okay, so now if I list, let's just,
Yeah, let's see if you,
let's just see, let's list it out. Okay.
J, which is, yeah, so J is actually inside, J is sitting inside of this ring R.
it might be called Jupyter Macaulay 2 or
Here, Macaulay
to
to
Jupyter kernel.
0.7. Okay, now, then the other magic
I thought.
indication is.
Okay, good.
Okay.
Now, if you do Jupyter kernel spec list or something like that,
It's too fancy for me. What is that?
oh, that just tells you what kernels
Well,
you got
if
installed.
I just start it, it should appear on the menu.
Yeah, yeah, that's true. I don't know if you do Jupyter Lab or Notebook?
I do Notebook, but you
Okay.
can launch Jupyter Lab. Like.
You can
not
go
that you
either
need
way.
Like Jupyter Lab is if you don't have an IDE.
Oh, I see,
You know,
okay.
Like, but if I'm writing Python code, I'm going to use my IDE to write the Python
Are
code.
these all,
Oh, no, these are just folders.
oh, I see, okay. Because that would be cool to have Jupyter,
Okay. So here, I'm gonna create, drama, okay? I'm gonna create a notebook. Oh, that's upsetting. It didn't, it automatically.
wait, select it, here, let's
Oh,
go.
I see.
Oh, there it is, M2.
Oh, M2. Okay. All right.
So it's not the default one in any case, which is, oh, you don't want it to
No,
be
but
the
that's
default
good.
one.
So what do I do?
Do capital R equals. And equals ZZ mod, 101. You can do it, and I think you have to hit Shift Enter, and you got it.
Works.
Yeah.
Flawless.
One thing I can't do though is I find extremely annoying in here is if the output wraps, I can't stop it from wrapping, line wrapping. And
There's
I think there's a way of doing it, but I don't know what it is.
series of options. There's view options in Jupyter. Like controlling the size of the output. So there's probably.
Where do I find that? I guess I can ask ChatGPT. That's how I oftentimes
Okay.
it told me to add some CSS. Here, I'm gonna get rid of my share screen. Are people online trying the problem also? The quadratic and P3 problem?
Difference between presentation and minimal presentation.
Presentation will give you, presentation of module doesn't change what generators you have. It just gives you the presentation matrix of it as it is. So but minimal presentation will say, well, you didn't really want those generators. I'll find a minimal set for you, at least if it's homogeneous. I'll do that.
Why would it give me an error? Like, maybe I can give it the right sort of thing.
Let me see.
Okay. So R is my quotient ring.
Oh, presentation of J. J is an ideal.
It doesn't like it.
So actually, you might need to change it to a module. So if you do module space J, it will think of it as a module. I forgot about that.
Module J.
Yeah, module of, you don't need the
Module
parentheses
M1.
of R to the 1, yeah.
Oh,
Or,
because M is okay. So I'm just using my weird.
oh, I see. Yep,
notation.
got it.
So there is a.
J. That should give it. No.
Oh, the MB extension. We tried that. Now that's what gave us lots of problems. But well, we used to use it in the old version, but then it changed and then it wouldn't Maybe that's all it needs is to be installed.
You have to see, yeah, somehow it didn't change, like when you did, presentation in J.
Oh, that's the other reason why this notebook is, why it's on a branch, is because on Ubuntu, they're still using the older version of Jupyter notebooks. So, and not Jupyter Notebook 7 or something,
So there we go. We got
or
that.
6 or
That
whatever.
matrix right there. And so,
Yes.
okay, so now,
Same thing I did.
yeah, so now what we want to do is we want to interpret this here. We can understand what's going on, right? So if you're going from R2 to R2.
Is everyone else okay working on stuff?
Right, so we take the map here, so anything. First.
Categorical way of doing things. So I'm gonna try to yeah, keep it more example oriented. I think that'll be better.
And then the point is, take image. Take all image. Take the image. Take everything. That should be. This should be. Remember? Remember what it is.
Is it working? Or you did you install that?
Here.
The extension? No. Want me to do it?
Well, what we could do is make a large example.
So, okay, so give me an example you don't like. You don't like.
Can I write it down?
Yeah.
I'm just gonna do the one I just did, but I can do it quick. Actually, I might as well put it all in the same node. There's that one, and then there's that one. That's matrix. B 3 by 3. And M2 is matrix J 3 by 3. And we'll let J be the ideal. M1 times M2 minus M2 times M1. Okay, so that gives us all of that. Now I'm going to change the print width equals 0. And now I'm going to do C is equal to res of J. Okay, and now I'm going to do C dot DD underscore 4. Ready? Yeah, so I would like to have a horizontal scroll bar on that.
I'm just seeing if there was actually built in.
Yeah, actually, that would be great. I very well could have missed something on that. I looked around for that, but I didn't see it. Yeah, so I could have easily have missed it.
The form, you're flipping everything around on your map.
When you do HOM of something comes something, you take the presentation matrix, you transpose it, and you take the kernel of it.
Oh, okay, so like I had the presentation of the J. Then you said I take the transpose.
Yeah, so when you do that, we've erased it now, but it's the HOM of J comma something. So you do it as J goes for, something maps to J, something maps to that. That's the presentation matrix. Now when I do HOM of J input, it transfers it around. So the dual is the kernel then of the map from the R2 to R2 in that case.
If I multiply these two matrices together, I should get. Yeah.
Wait, what?
No, I was just wondering if I should be able to see it very easily, right? So this is the resolution of J inside of this right here, and this is the HOM. And I was just wondering if I can see it from here.
That's only part of the resolution, by the way.
Yeah, because it keeps going, right?
Yeah. I actually on the problem I asked to find the resolution, but if you look at it, you see that it's there's actually a major theorem staring you in the face.
But,
Sir?
it must repeat, right?
Yeah, it's hard to tell. Oh, no, you've got the matrices there. Yeah.
Yeah,
So let's see.
show the repeating part, right?
Um, actually, that's
Oh, yes, it
interesting.
does.
Does it?
Yeah, so the first two don't repeat, and then the last three form the repeating.
Oh, there,
Yeah,
yeah, okay, I see
yeah.
it now. This one and that one. right?
Yeah, when you only have that many, I mean, if you do it to length limit 10, then all of a sudden
Okay.
it
So what this is saying, so to make sure I understand how this is all working, because we know that like this bit here, it is repeated here, we know that the next one afterwards is gonna be this one, and then it's just gonna go tick, tick, tick.
Yep,
tick, tick, tick.
exactly. So every other one is the same. So it's periodic.
Yeah.
And that's the theorem of Eisenbud from, I forget when, early 80s or late 70s or something like that. It started the whole matrix factorization thing. So
Mhm.
Very good. Very good. I'm just reading on, okay.
how are people doing? Should we talk yet, or do you want to? It's fine to work on it more if it's being useful.
We'll try the second.
Here, while we're doing it,
This is the image.
yeah, that's an old extension. Unfortunately, it might have moved. I'm not really sure. I couldn't get it to rework again.
Yeah, so changing.
It became serialized.
Yeah.
I'm getting confused by the twisted cube example.
Yes. Okay. Which question was that?
No, I'm looking back at the beginning.
Yeah. Okay.
So this was the definition of a presentation. It's the phi here,
Yeah.
and then here it looks like it's M is R mod I, and then we got F, G.
So actually,
Why
the
is phi here?
presentation of R mod I is this.
Oh, is this one?
Yeah. The
Okay,
presentation of I is this one,
I see, okay.
because R3 maps to I, because I mean, this map is onto I.
Okay. This is the presentation.
Of R mod I. Yeah, so R mod I is just given by the generators of I, a matrix.
Okay.
Whereas I has more involved.
I was like, there's an off by one error somewhere.
Yeah.
Thank you.
Oh, it is?
Yeah.
I didn't see it.
The module from that.
Oh, actually, yeah.
Oh, I think you should use XW, no?
Yeah, well, I did that stuff.
Mm.
That's not. But we wanted.
When you guys are ready, we could actually play around with it together also. But but if it's being useful right now, to do it Are you ready to do it, or are you working on stuff yourself? Yeah, okay. I'll get it ready here. Okay. Okay, I will share my screen here. Should we talk about the first problem? So Macaulay 2 has several types of modules. One of the ones we were dealing with in the first hour were all co-kernels of things, but you can have image of something that's a perfectly fine module as well. And sometimes it's better to use that. Like an ideal is an image of a matrix, whereas if you write down the presentation, you can't tell it's an ideal, and so on. So that's can be a little. You can still do that, and it will say, oh, rats, I really want a presentation for that, so I'm going to compute it. So it does do that. The output, yeah, I mean, that's right. And you can always do prune of it if you want to get the presentation of it. Although that prune you can actually type presentation if you don't want to change, you probably want to just do presentation. Prune of it will change the presentation, and then you're not sure how it matches with what you have. Yeah. Okay, so let's do this thing here. So I wrote some of the stuff down here, so I can just type it in. There's my polynomial ring. I guess I called it the polynomial ring S. Oftentimes, if it's homogeneous, I use S as the polynomial ring, and then R is the quotient. An ideal of J comma X comma Z is just this. Notice an ideal of R. You have to pay attention where it is too. Depending on how you define it, it could be an ideal of S, and you'll get totally different answers. Okay. However, notice that you can do Grosvenor basis of it over that, and it's giving X and Z. So what is it really doing? What it's really doing is it's sort of like doing a Grosvenor basis of the whole thing, including the ideal that you modded out by, and then ignoring the polynomials that you modded out by. So in fact, there's a theoretical way to say that. But
Mike, can I ask you a quick question? Sorry.
Sure.
Yeah, I don't know if this is obvious or not, but is the resolution of J as a module different than the resolution of J as an ideal over this ring?
yes. So the resolution of the module is just what you would think. The resolution, if you do res of J, what you really get is a resolution of S mod J or R mod J. Okay, does that make sense? So in other words, it's just it's one of those things that commutative algebra people do. Is they oftentimes, when they say I, they oftentimes mean the ring mod I. And as I said, I used to hate that, but kind of embraced it now. Okay, so here resolution to length 10. I just chose the 10, and it's 2, 2, 2, 2, 2 out as far as the eye can see. And here's our f dot dd is going to tell you what all the matrices are. And if you look at the beginning, xc, then something, something, but all of a sudden, somewhere along the line, they start repeating. So here, let's see, this one, you get this, ywz, okay, that's not the same as this one, although actually it's pretty close. But they're exactly identical from here to here. So every other one is, once you have two of them and you know the kernel of the other one is the first one, then you know the resolution, period, even if it's infinite. Yep. Yes. peak, I don't know what peak does in this case. If I do peak of F, I just get, yeah, you know, the thing is that peak in this setting, turns out it gives you this, but it would kind of be annoying too, because, it also is showing you the innards. By the way, the new complexes package that Greg Smith and I have written and are incorporating in Macaulay 2 is that will be the default before too long. You can't see it like this. I mean, you can do peek of it and you will actually see something reasonable. You won't see all this cache complete. Actually, you might see the cache, but you won't see all this other stuff because it'll be done differently. It's stored internally in a more sensible manner. Okay, anyway, so if here is F again. So this is, notice what I did res of J, but you can see the last matrix is R2 to R1, and the co-kernel of that is going to be R mod J. So which one of these matrices is the presentation of J? Yeah, it's 2 to 1 right here, right? Because this map, the image of that is I. So this map R2 maps onto I, that's a surjection, and then this maps to the that. So
What's I, sorry?
J, sorry, J. There is no I. I is my, you know, my generic ideal. So not anyway, whatever. So here's the matrix. Ignore these are degree things, but that's really not relevant for this problem. And but you can also do that will give you it, but you can also do presentation of module of J, which gives you something different. Now, why is that? Well, the presentation of module of J, this I think actually exactly matches the generators. Well, no, it's just choosing a different basis of the kernel of that map. So notice that it's just swapped the order, actually. That's all it's done. And that's certainly something that you can do. So the presentation matrix is just annoyingly not unique. And in fact, you can see it here. If I give 2 different ways of computing it, it will choose different things. Yeah.
So when we do with Grosvenor bases, we like reduce Grosvenor bases for the uniqueness. Is there something that we do with presentation matrices?
No, not really. We could, but even there it's tricky because if you have the generators be exactly the same, then I could do gens of GB of that. Like for instance, if I do that, what do I get? If I do gens of how about Grosvenor basis? Grosvenor basis of 09, okay? It gives me that. How about of 010? It obviously didn't work so well. Maybe if I do, oops. If I do Grosvenor basis of image of that, an image of 09, those are different. And, you know, the trouble is, I think it's and that is a Grosvenor basis, but I don't know. I think it's using a different monomial order. I'm not sure actually.
Is the first thing it's doing just computing the S pair and saying, well, that goes to 0, so I don't do anything?
Yeah, but the Grosvenor basis here, if I do gens of GB, this better be, there's that in 010. Yeah, they're different. Somehow I would have thought that it would normalize it. If I do lead term of O, and if I do lead term of 015, I'm not sure. It seems like a bug to me. I'll have to look into it. Anyway, so now if we have the presentation, if I transpose that presentation matrix and take its SIS, that is the presentation. No, that is not the presentation. What is that? That's the generators of HOM, right? So, whoops, I lost my. So I have J mapping R2 to R2, right? And I don't know what this is. Let's call it F. And now I do R2 to R2 and call this F transpose. And here is Hom of J into R. So it's the kernel of that. Oops. Okay. So now we want a presentation of it. How do we get a presentation of it? So I take F, I take cis of it, I get this thing, right? So what is cis of it? But it's really a map R2 to R2, which maps onto that. This is the sub thing of this. So cis, this is cis of F transpose, is this map. So that gives me the generators of this. Let's see if what it looks like here. So if I do cis of actually, where is this the matrix M1? Actually, now I'm confused. Okay, let's go back to, here's the presentation for J. And here I take the transpose and I take cis of it. So the columns of this are going to be the generators of Hom of J comma R. Does that make sense? Do you know what that element means, X and Z? What is an element of Hom, actually? This is something we didn't say earlier. We just did the right exactness or left exactness and stuff like that. But a map from Hom of JR is a map that tells you it tells you where the generators of J go here. And the first map here, this XZ, that's the first column, is the first generator, is saying, that's the map that sends X. Remember, the ideal J was just X and Z. It's sending X to X and Y and Z to Z. So it's the identity map. The other one is sending X to W and Z to Y. So that's a different one that happens to work here. Okay, so those are the two generators of the Hom, and if I want to get the relations on that, I just need the kernel of that map, that cis F transpose. So I can do cis of that. So here I can do, instead of this one, I can do, let's call this one here. Let's call this gens of J dual. Okay, and now I'm going to do cis of that. Gens of J dual. And that is the presentation matrix of the dual. So is that different? Let's actually think about that. What is the presentation matrix of J? Can someone tell me? Is it on the board? Or did anyone compute it from earlier?
First column, Y should have. I don't think it's a.
And then J dual, what's its presentation matrix? So they both have two generators, right? So because it's going to be 2 by 2, they're going to have two generators and two relations. So what is this one? Actually, it's on there, right? Y negative Z negative W X. Okay. So there's that, it looks a little different. It's a little hard to tell if it's different, to tell you the truth, because maybe there's a change of basis that would make it the same. You know, it turns out there's not. Okay. But now what's the next question on the sheet? Okay, this is J star. So this thing here, actually, this is F here, and this is F transpose. At least if we did it right. And then you take, and then this cis of F transpose was that matrix. This should be the. Let's actually write these down and see if that makes sense. This thing here is what? Is the transpose of this. That's Y minus W minus Z and X, right? And if I take the kernel of that, I'm getting that one up there, I think. X, Z, let's see if it matches. X, Z. I don't think that matches. I think I've got the different presentation. So let's actually do this slightly differently. let's do F, which is what we're calling it, and we're gonna, that'll be the presentation matrix of the J. So that's what it is here. Y minus Z minus, that is exactly that, okay? And now I'm gonna do F transpose. I'm gonna just try to do this carefully. I'll try to put this on afterwards too. F transpose is equal to transpose of F. Okay. Okay, so so let's see. Over here, oops, I have the okay, so here's F and F transpose on the same line. That looks good. And now I want the now the next one line would be gens of J dual. Let's get rid of this line. Let's just say that's the kernel or cis of F transpose. I would just, in Macaulay 2, I would just use cur, but cur gives you an image. It gives you a module. Cis gives you the generators, the matrix itself. So here, the kernel is generated by these columns, X, Z. So hopefully that is, if I take that times, now is that true? Let's give that a name. We have that a name. Okay, so that if I take, now which way does it go? If I take gens J dual and I multiply it by FT, I get 0. What if I did it the other way? Actually, in this case, okay, which way is it for real? That's the gens J dual right there. And then that's the other one. So when I multiply, that's the one on the right. So that's this, the second one is what we're really doing. Is that map times that map. And that's 0, as it should be, since it was computing the syzygies. The only reason the other one's 0 is because of this periodicness that's happening. Okay, but now we want, so now we have this matrix down here, which is XZWY. So this is WY. Now let's just make sure. So it multiplies the opposite. So Y minus W goes here, and sure enough, we get the quadric, and that's 0. And this one is just the Cazul syzygy on that, so it's 0. And similarly, this one against the first is the Cazul syzygy, and this one times this is the quadric. So they're all 0, and that turns out to be everything, which needs proof, or it's not completely clear that that would be everything. Okay, but that's just the generators. Now we need the relations on these things. Well, if I have a bunch of columns and I want the relations on them, I just take cis of it and get the syzygies on those things. So I just do cis of gens J dual. And this is going to be presentation.
Joule.
J dual. And I'm going to call this presentation of J dual is equal to that, okay? And that's what I get as the presentation. Y minus W minus ZX. Now, is that what we had here? Y, no, it's not. Y minus W, yeah, it is. Okay, good. So these are the things that we're getting. And now, these are two things. Now, what's the next thing I had asked? I said, find an ideal such that this thing is isomorphic to that J star. So how do you do that? I want J star to be an ideal. So here's one kind of sneaky way you can do it. So basically, I want J star mapping to R, and I want an inclusion like that. If I do, then that will be isomorphic to the image, which will be an ideal. That's an element of Hom of J star into R. So now I can I can take the kernel of this, and that the columns will give me the elements of that. So what if I do the kernel of that? So if I do cis of that presentation matrix, oops, I already have that down here. No, that was something different. So if I do this, I get this. So again, this is now sending, this is, wait, that's not right. xz. Oh, no, I see what I did wrong. So it's not cis of gens, so first of all, I'm doing the wrong. I have this, when I take an ideal and I want the dual, the Hom of that into that, I have to transpose it first, right? This is very confusing. So in here, I want to do a cis of transpose of that. And now I do it. And now it's the first generator would map to it would send something to X and to W or to Z, Y and Z. So in fact, what you can do is choose any sort of generalized column. Like I could choose X comma W would be an ideal, or I could choose Z comma Y. Those would be ideals that you could map this to. Those are the same ideal in this, or they're isomorphic ideals. And but that's different. Okay, so remember J was this ideal here, and J dual is isomorphic then to either X comma W or Z or Y comma Z. Okay. Do you see why that is from that? Because I have two different maps from J star into R. One of them is the map given by the first column, XW, and the second one is the map given by Z and Y. So the image of that map is going to be either, if I take the first one, it's going to be the map, the image is going to be one. If I take the other one, it's the image is the other. We don't know it's an isomorphism onto the image. We have to make sure the kernel is not zero. But we can do that. So I mean, that's actually not so bad. So we get these things. But take a look at these things. Is this the same ideal? I mean, this is, if I take the zero set of this, I'm getting another line. So here I'm taking a line, let's call that line L. And let's take a line M. Maybe M is a bad name. Let's call it L prime. And that's the zero set of this X and W. So these are two lines on Q, and where do they intersect? If you have two ideals, they intersect, you throw in all the ideals together. So you have X and W, and you have X and Z. So X, Y, and Z are all zero. That gives you that X, Z, and W are all zero. So Y can be anything, which since it's projected, that means it's the point. It's a point. So basically, L intersect L prime is equal to a point, P and P. And sure enough, these are on opposite rulings. So you have one set of one ideal rulings of lines, and the other. And this process takes you from one ruling to. Anyway, that's sort of so the point is that all of this stuff actually, and when we do divisors, we're going to see what happens. This J star is essentially taking the negative of the divisor. So that's a line. This is taking negative line, but only up to the hyperplane section. So it's really the hyperplane section minus the line, which is the other one. But anyway, this is this was just supposed to be the start of doing the algebra and seeing that it will have a lot to do. Any questions?
Anything special about the ideal that every took any line on the quadrant?
If I take any line on the quadrant here, I will get depending on the isomorphism, I will get I will get a line in there. Now, actually, it's an interesting question. All the lines are actually isomorphic to each other in one room. So these two ideals are actually isomorphic as modules. Does that make sense? But, you know, and in reality, that's going to be like when you do linear equivalence, that's telling you that they're linearly equivalent. But anyway, so Okay, I suggest, we don't actually have that much more time. But I wanted to, I really do want to talk about the relationship of modules and coherent sheaves. We won't get to the, we won't get to the cohomology part yet, but that's okay. It's probably good to spend a little bit more time on that. Okay, so for the remainder, let's talk about coherent sheaves on projective space. Okay. And this will include all coherent sheaves on all projective subvarieties, all projective varieties. Projective variety is just the zero set of a homogeneous ideal in one of these spaces. Okay, so this is a huge amount of sheaves. Now, if you've ever dealt with sheaves, there are other sheaves. Okay, there's constant sheaves and other things that are not like this, and so we're not handling that. But this handles a lot of ones that are very geometric in nature. So here's our notation that we will use for this whole game. Pn, we're going to let S be K of x0 to xn. The exact field that we choose turns out not to play much of a role here. This is the homogeneous coordinate ring. Okay, so if I is contained in S, it's a homogeneous ideal. We get the zeros of it, which I oftentimes write this way, is a subvariety of Pn. Okay, so this is a set of all points in there that vanish at all these points. Or is it? So there's two ways of playing this game. One of them is when you, in algebraic geometry 1, this is just the zeros of all those polynomials as points in here. Once you do schemes, you could think of this as the scheme corresponding to this ideal, even if it's not a radical ideal. So if it's a radical ideal, everything's the same, but otherwise you might want to consider that. For what we're doing here, probably wanted to think of that as the scheme thing, but it doesn't really for what we're doing. Okay, so this is kind of cool. So if you have a homogeneous ideal, you get that. This isn't an example of a module, but now I want to consider graded modules. For now, I'm just going to say there is a little annoyance with sometimes you hit modules that are not finitely generated, so you have to play around with that. But consider graded finitely generated S modules. Okay, and now here is the fact. So there is an operation. So I'll call tilde like this. And with that sends M to some object to M tilde, sending these such modules, sending graded finally generated S modules. And the output is a coherent sheaf. M tilde is equal to a coherent O of Pn module. Okay, or a coherent sheaf on Pn, same thing. Okay, so if you're familiar with this language, awesome. If you're not, who cares? It's just some words on the page. Okay, what's important is that this process. So here, let me write down this. Let me give myself a little bit of this.
Sending graded finally generated S modules to M tilde.
Oh yeah. Got ahead of myself. right? Sending graded finite generate modules to M tilde. Sending a graded finite generated S module, M, to M tilde, which is a coherent PN module. And then the properties of this are the following. It's actually quite easy. Once you know the definition of a sheaf, it's quite easy to write this down. Okay, so, and the properties are the following. One, all coherent OPN modules, all coherent sheaves on PN arise in this manner. So you're not losing any, so instead of looking at some subset of these things, this really gives you every single possible sheaf on PN that is coherent. Coherent basically means it comes from one. And that's what this is. So this is not like this isn't rocket science. This is just a question of me trying to avoid the whole language of sheaves. Okay, so the second, there's other properties that are important, but first I want to say what some modules map to. S, that module there, tilde. If I do S tilde, that is OP of N. So this is the sheaf of rings of projective space. If X is equal to the zero set of I, it's contained in Pn, then S mod I tilde is equal to OX. This is meant in a scheme theoretic way. In other words, if this is a radical ideal, it's fine, it's whatever it was. But if otherwise so the sheaf of rings is always of this form. Remember we did shifting of modules. So remember we had M, if that was M is greater than or equal to M sub D for D and Z. Then recall, so if that's that, and M shifted by, that's E, I guess. That's equal to the same thing. But the things in degree D in this thing are equal to M in degree D plus E. So it's the same module, but just shifted over a degree one way or the other. And if I always have to figure out which direction. Okay. So this is the sum over all D and Z and sum over all D and Z. So if we have this, we get a new module, and the sheaf that you get from it is different. Then if I take M tilde, sorry, M of D tilde, this is equal to O of it's equal to M tilde, and then there's a notion in sheaves of twisting, and that's the same, that it matches. This looks like there's there's no content here, but there is. This is an operation on modules, and then this operation on sheaves, and they correspond to each other. I mean, it's not a huge amount of content, it's pretty easy. Yes. Okay, what other things do we have? There's a couple really important ones. Okay, so this is just a few examples to sort of get you, that these modules really, when you see sheaves, it's just the modules. Okay, now, yep.
Well, 0.3 is any ideal like this we have, right? All fits in the same.
No, this is if the ideal of X is equal to I. In other words, there's only one ideal that does it. Oh, okay. So if it's radical, you want the radical ideal. Otherwise, you're getting some fact thing. So this notation of sheaves is really, if this is not reduced at all, then this will be different than if it's reduced. Yeah, sorry, I wasn't very clear about that. So the next one is that if M is a module, say MD is equal to 0 for once you get large enough. Okay. Then, in fact, M tilde is 0. It's just, that's it, it's gone. Okay. The next cool thing is that if, well, I don't need to say this. This is an exact function. It sends, i.e. it sends a graded exact sequence. Now remember, so all the modules have to be graded and all of the maps have to be of degree 0 graded. So graded exact sequence of modules to a graded to an exact sequence of sheaves. Square sheaves. Okay, that's actually really useful for proving things, and for computing things. Actually, not proving things so much, but and I think those are the main things. So I'm going to do an example of it. How are we doing? Okay, good. So let's take our trusty example, which is the twisted cubic. Okay, so let's take the twisted cubic. And that's going to be, given by I, which was the I2, the 2 by 2 minors of that matrix ABC, BCD, where S is equal to K of ABCD. And V of I is going to be a curve, we'll call it C, inside of projective 3 space. Okay. Then we have the following, we already know, we have 0 to S mod I, to S, to S minus 2 to the 3. There were 3 quadratic generators. And then this one was the matrix ABCs. This is the F1, F2, F3. And this is the matrix ABC, BCD. And this is these are linear, so that's minus 3 to the 2. So that is exact. So I can just tilde it now. So apply tilde. What do I get? I get O of C. S mod I is tilde is O of C. This is O of P3. This becomes O of P3 minus 2, 3 copies. And this is O of P3 minus 3, 2 copies. You might say to yourself, okay, that looks pretty much the same thing, okay? And it is the same thing, but it turns out that this bit here is the key. This thing here is saying that if you happen to have a module that is 0, not 0, but if it's 0 eventually, then when you sheafify, all of a sudden that can simplify. So for instance, here's another example. Maybe I should have done this first. Would have been a better example. Let's take S is equal to K of XY, corresponding to P1, okay, projected. And now what I wanted to take is the ideal XY then. So I have 0 goes to S mod I. So I is equal to the ideal generated by X mod I. And this is going to be that to S. And now there's 2 generators, S2. That's X and Y. And now, but there's a -1 here because of the shift of the degrees. And now there's only one syzygy on those. that's y and minus x, that's the causal syzygy or trivial syzygy. And that goes to S and X too. Okay, now let's sheafify this guy. Okay, apply tilde. What is this one sheafify to? Well, once I mod out by x and y, this thing is just non-zero in degree 0 only. What? Oh, so that's a 0. And that's an OP1. And this is OP1, 2 copies minus 1, and OP2, P1 minus 2. So that's exact. Actually, it's going to even be better than that. But anyway, so we things simplify. So in some ways, you can the way I think about it, sheaf cohomology or sheaves in general is that you're just anything that is supported at like Artinian type things, like at the ideal where it's in the empty set, just goes away when you do this process. So that might not seem like a whole lot, but it's coarsening enough of your data that you can actually sometimes prove much better things than you could when you had all the complicated detail around. Here's an exercise which I might actually put on the list. I'm going to probably change the list up around because we didn't quite get to some of the stuff. So let's let M. So if M is a graded module, I can do this greater or equal to D. And I want this to be equal to the direct sum over, maybe I should greater or equal to E. This is going to be the sum of MD, but only the ones of degree at least E. Okay. So this is the truncation. Let this be the truncation. And degree D. So then what? Then A, M tilde is actually isomorphic to M greater than or equal to E. So that's actually not so hard to prove because you can write an exact sequence. This one sits inside of this, and the co-kernel has this property that it's 0 in degrees at least E. So then you sheafify and you get basically it. Let's say truncation at degree E. It should say that. Because otherwise it's just incorrect. Okay, so yeah, I switched my D's into E's. Okay, so anyway, so there's that. That's A, and B, how do you tell if two things are isomorphic? So I haven't even told you what maps are between them, but essentially, if they're free module, I mean, they're all going to be just induced by matrices like that. Any R module map will give you a thing, but in fact, you can have these things be isomorphic in little cases, in part because of this. These are not isomorphic at all, and in fact, if I have a map, there is no map from M to M greater than or equal to E. There just isn't one, and so it's not going to be the case that you just take it and sheafify it. So what you get here, though, this is true if and only if there exists. I'll change it to E in Z, such that if I truncate M in degree E and I truncate N in degree E, those are isomorphic. Are isomorphic as graded as. By the way, I'm doing everything with just the polynomial ring. All my ideals are going to, I'm not working mod those things ever, just always working. So this is actually pretty cool. This tells you pretty much exact, in fact, any map between one of these things is the way you give a map between it is you find truncation and give a map here. That will always be the case. So not sure that's as easy to prove. I don't want to, I'm not going to go on to do any sheaf cohomology stuff. But basically, sheaf cohomology is just going to be, are going to be axes of some sort. Okay, but I do want to say something about what some other things sheafify as. So if I take, so here's another example which we can't quite prove yet. Not sure we will prove it in this, but if I take, let's let x equal 0 set of I, but what I really mean is that I is equal to the ideal of x, and this is sitting inside of projective space. Okay. And to tell you the truth, I might want it to have some nice properties to it as well. I can certainly do it. Let's suppose that in fact x is irreducible. So it's I is a prime ideal. Okay. Suppose x is irreducible reduced of codimension C. And then if I take x C of S mod I on an S, there's a little bit of a shift degree here. So this is a nice module, one that we've seen how to compute and everything. Take a free resolution here. This is changing grading in an annoying way. You have a 50% chance of getting the sign change of it correct. At least do it randomly, but if you do it from your own intuition, it's probably we've got a 30% chance of getting it. Okay, but anyway, you can get this, and if I sheafify this, this is equal to what's called the canonical one. It's kind of weird, actually. This really allows you to do lots of geometry on the right using algebra. So that this will be pretty good. Another thing is, well, no, I guess we need sheet. We have about 8 minutes left, I think, but I think 3 hours is a long time. I think this is probably a good place to stop. I think next time I do want to do the sheaf cohomology, and the way we're going to do it is I'm going to define what it is, but in algebraic. But it's going to be an infinite algebraic. And then I'm just going to state some things, which I think if you go puzzle it, you can actually figure out how each of these things. But if I take the whole time to prove it, it won't quite. So, and then we'll do examples of computation. And there's going to be several ways of computing sheaf cohomology. We're going to use the stuff from Serre. Serre's 1955 paper FAC is the most amazing paper. It's the first computational algebraic geometry paper, computational modern algebraic geometry paper, because he shows how to compute all these things. And it turns out that it's really great. It works in this case. It doesn't quite work if you extend it toward varieties, things like that, but there are things you can do. But there's another way of computing sheaf cohomology that's totally awesome, called, that goes through the BGG correspondence, the Bernstein-Gelfand. And I kind of want to go through that at some point. I think right now at the beginning, I do want to go through and do some stuff with primary decompositions and integral closures first. That'll be away from the module. Then we'll get back to ideals and things like that. But we'll be more into how the algebra, how the algebra corresponds to the geometry. So some of the problems that we did earlier with maps of kernel of ring maps and things like that will become a little bit. And so I think next, I have to think about how I want to set it up. Whether next time we're going to do first, I think we should probably do a little sheaf cohomology first. That'll be the plan. Anyway, that's all for now. So I probably might rearrange the homeworks that you want, but we didn't go through any homeworks today. Did anybody have any that they wanted to present? Not right now, obviously, but just for future, for the next time or something like that?
We're gonna talk about the Benny table.
I want to talk about the Benny table. Yeah, in fact, I'd rather talk about the Benny tables than go. What I was thinking of, by the way, well, no, how many people here are actually taking the course? 1, 2, 3, 4, 5, and there are 3 people online, I think, taking it for granted. Is that right? Maybe. Okay, so, but what I was thinking of is, so, do you need, is a satisfactory, unsatisfactory fine, or do you need do you need an actual grade?
Yeah, don't grade anything, that's fine.
That was totally my, my
I think
thinking.
you said that in lecture 1.
Yeah, right, okay. So, I mean, what we could do is if people, like, one option is if people want to write up solutions to the problems, then we can always swap it around, have other people look at it. That's actually a very valuable thing. If, when you start reading someone else's, you're going, oh my God, now I understand why no one can read mine. And, so that's pretty useful. But anyway, I'm not gonna worry about it. Okay, great. See you all next week. I forgot one more thing. So there's gonna be a number of people here working on Macaulay 2, starting Thursday, Friday, and next Monday, Tuesday. We're going to sometime during the day have a like a Macaulay 2 question and answer period. Not just sometime, but maybe even each day. And then this is a great time if you want to try to get your setup all really nicely set up, or you want to learn more, or you just want to play around with it and be around where we can ask questions or something like that. That would be I think a pretty good. So, there will be enough people around that know a lot about it. Either how to do something mathematically or how to do it. Probably the use of it.
Mike, sorry, just a handwriting question. This last example is in PN, right?
PN, yes,
Okay.
right over here.
That determines the
The
shift.
only
Yeah.
thing where it matters is the codimension, because it's not the end of the matter. And the end the shift.
And then can I double check something I think you said just in passing, but you said all Artinian modules sheafify to 0 just based on this fact that you had written?
That's right. It's actually kind of interesting. Yeah, there's a way of going backwards, but it doesn't always take you to finally generated things. Oh well. Okay, good. Okay, thanks.